Good day. My name is Natalia Kosheleva. I am scientific researcher in the Institute of Continuum Mechanics of Russian Academy of Science, and I would like to present you a work titled On Application of Distributed Force Embedded into Material for the Mechanical State Monitoring of Civil Structure, which was done together with my colleagues Valerii Matveenko, Grigorii Serovaev, and Georgii Gusev. Structural health monitoring systems allow for a timely assessment of the structural integrity and therefore increase the operational safety, optimize the economic cost associated with repairs, and extend the service life of various structures. In this regard, research related to the introduction of more advanced and effective monitoring systems, ranging from the simple and sometimes inefficiently effective to the ones that utilize sensors that can be embedded into the material at the manufacturing stage of the structure, is a great of importance. Fiber-optic sensors are immune to electrical interference and under harsh conditions can offer certain advantages over the other sensors, sensitivity included. Also, fiber-optic sensor can be easily integrated with the other equipment for remote monitoring and allowed observing structure during all stages of its manufacturing, design, testing, operation. Nowadays, FOSs have a number of applications in different areas that are shown in the slide. The classification of FOSs are shown on the slide. In our research, we will pay attention on the distributed force based on relay scattering, and also we'll use the point force based on the break gratings in order to make a comparison of the measurement received from distributed force. The operational principle of distributed force based on the relay scattering are shown in the slide. This technique relies on the frequency modulation. The instant light wave is a quasi-continuous wave whose frequency varies linearly with the time. The Fourier transform on the backscattered signal corresponds to a temporary trace of the intensity of the backscattering. In this work, an open-air backscatter reflectometer by Luna Innovations was used to carry out distributed measurements. The report will be divided at two parts. Firstly, the mechanical behavior registration during operation will be taken into account, and secondly, the defect registration using force will be shown. A prismatic shape sample made from the cement mixture was selected as an object of study. During the preparation of the sample, a distributed optical fiber and the point force were embedded into sample as it's shown in the figure. After placing the fiber optic lines with the tension necessary to maintain the straight line arrangement of the fiber, the mold made of moisture-resistant plywood was filled with the cement mixture. To create a cement sample, Portland cement 400 and river sand was used in the ratio of 1:5. An attempt was made to embed an optical fiber that doesn't contain additional protective packages except for the standard polyimide coating. This it was possible to avoid and the additional recalculation of the strain values obtained with the force, which is necessary to restore the real strain distribution picture of the controlled material. The next stage of the study is related to the strain measurement in the manufactured cement and the external loading according to the three-point bending scheme shown in the slide with the help of embedded force. In the course of the experiment, a stepwise increase in the load was carried out with holding the constant load level at each stage for 2 minutes and unloading before each stage of loading. The obtained experimental results from FOSs were compared with the result of numerical simulation by the finite element method. The high sensitivity of the FOSs should be noted, which make it possible to measure even small levels of strain. The experimental results showed a close to linear behavior of the material at these load levels and a good agreement with the result of numerical simulation. In the slide, the strain distribution along the optical fiber is shown. At the left picture, the solid line shows the strain distribution at different load levels along the line of the optical fiber embedded in the material, obtained using the finite element method. At the right picture, the solid line shows the strain distribution at different load levels along the line of the optical fiber embedded in the material, obtained using distributed force. The points correspond to fiber break gradient sensors. Operability of distributed fiber optic sensors are shown in the slide in tension and compression zone during bending test. Structural health monitoring system should not only be able to measure strain at different locations of the structure under operation load with a high reliability, but also have the ability to detect the appearance and development of defects with the help of applied sensors. The defect detection approach is based on the registration changes in the strain field introduced due to the defect appearance using embedded sensors. To assess the approach efficiency, a series of experiments was carried out with imitation of the crack appearance in the sample by introducing the cutout. During experiment, the length of the cut was increased from 5 to 15 millimeters in several stages, and the sample was loaded with the force of 403 newtons according to the scheme. Analysis of results obtained by distributed FOSs shown that the location of the crack shifted from the center along the length of the sample. The point FOS also proved this statement. Since the introduced defect is located between sensor 1 and sensor 2 of point sensors, the sensor 1 also effectively registers the appearance and growth of the defect, while the readings of sensor 3 are weakly dependent on the defect appearance and growth in this size. Conclusions. The possibility of using embedded FOSs for recording the mechanical behavior and state of the cement sample at different stages of the life cycle of a structure have been demonstrated. The result of measurement by distributed force by point sensor based on the Bragg gradients and the result of numerical simulation shows satisfactory agreement when loading the finished sample. The possibility of using embedded distributed force for recording the appearance and development of defect has been demonstrated. Despite a number of limitations, the considered approach can be used for various laboratory studies. Thank you for your attention. I will be happy to answer your questions.